This is Premier Aerodynamics podcast number 30. Yes, we've done 30 of them, and to celebrate, we're going to give each of our listeners $30 worth of respect. So this is how $30 worth of respect feels. How does it feel? Let us know. Anyway, today we're talking about how the turbulence intensity at low Reynolds numbers affects airfoil performance. To do that, we're going to look at a paper called Aerodynamic Characteristics of Different Airfoils Under Varied Turbulence Intensities at Low Reynolds Numbers. And the reason why this is important is because if you've ever looked at any graph showing how an airfoil performs, chances are you probably will see different Reynolds numbers. And the reason why that is because at different Reynolds numbers, the airfoil will perform differently. Typically, you'll get a higher stall angle and sometimes even a greater lift coefficient along the way, depending on what flow physics you get, as we'll go through. So the Reynolds number is very important. Now, the interesting thing is that the turbulence intensity of the flow impacting the airfoil is also very important, because you can effectively mimic a higher Reynolds number with a higher turbulence intensity. So if you have an airfoil at 1% turbulence intensity, that might, and let's say you have a Reynolds number of 100,000, if you bump it up the turbulence intensity to, let's say, 10%, that's going to mimic something maybe at 500,000, for example. Just the flow physics, because turbulence intensity in effect determines how much disturbance is in the flow, and that then affects transition points along the airfoil, affects separation points, affects the boundary layer, whether it's very slow moving near the surface, whether it's very fast. That then affects how the adverse pressure gradient affects that boundary layer deceleration. So the turbulence intensity is very important, and you need to make sure that when you're doing any experiments or any CFD, that you get it right. Because if you do experiments, for example, to validate your CFD, but you have a different turbulence intensity, then you're not going to get your CFD matching your experiments. And that's one thing that's really important to keep in mind. For example, I remember like maybe about a decade ago now, I was using some CFD software and I wanted to validate it with my wind tunnel experiments. And my wind tunnel had a turbulence intensity of like 0.6%, I think, from memory. The CFD package that I had only had 3 settings for the turbulence intensity. It had 0.1, 1%, and 10%. So it was really not ideal, because even at such a small difference in turbulence intensity, it does make a big difference to the airfoil performance. So you need to make sure that you get the same turbulence intensity, and try to change the turbulence intensity in a wind tunnel is quite difficult. You can take out mesh screens, but then you have to put a hot wire or whatever in there and measure the turbulence intensity, and you don't get to change it to whatever you want. You get discrete levels. Like if you have 3 screens in there, you might get a certain turbulence intensity. When you put 4 screens in, you get a different one, and you can't really, it's not a continuous scale. You have discrete levels that you can put it at. So making sure you understand how the turbulence intensity affects not just airfoils, but anything really in general is very important, because then that means you can actually do your experiments better. You can actually validate CFD better, and you're not wasting time or money. So this is a very important topic. So let's get into how turbulence intensities affect airfoil performance. So just looking at the abstract quickly to give you a good overview. They said that the effects of, this is a paper called, I think I mentioned it already, but I'll mention it again just to make sure. The link is in the description. It's called Aerodynamic Characteristics of Different Airfoils Under Varied Turbulence Intensities at Low Reynolds Numbers. It's open access, so you can access it yourself. In the abstract, they give you an overview of what the turbulence intensity does. They say the effects of varied low Reynolds numbers and turbulence intensities on the aerodynamic performance of a NACA 0012 and SD 7037 airfoils were investigated. So just right there, the NACA 0012, this is a very common airfoil, like one of the most common that you're going to use for learning purposes and even research purposes. It's a symmetric airfoil, and the thickness is 12% of the chord. The SD 7037 is a little bit different. It's a little bit more of a niche airfoil. It's fairly thin. It has a thickness ratio of, I think, 9.2% or 9.3%, something like that. So it's fairly thin. And it has a camber. The camber is, I think, 3.2%. So not that much camber, but a little bit. So there's fairly different airfoils. One is uncambered, the other one is cambered, but they have similar thicknesses. They go on in the abstract and say the results show that higher turbulence intensities or Reynolds numbers lead to more stable airfoil aerodynamic performance, larger stall angles, and earlier transitions with a different mechanism. So this is all very important that we'll cover. the different mechanism, what they mean is the mechanism to turbulence. So the boundary layer transition differently, and we'll get into that. Generation and evolution of the laminar separation bubble are closely related to Reynolds number, and it would change the effective shape of the airfoil, having a big influence on the airfoil's aerodynamic characteristics. So if you haven't listened to other podcasts that we've been kind of on a string of these podcasts now that they involve laminar separation bubbles. I don't know why we've just gotten lucky and they just keep on doing it. For example, podcast number 11, which is called NACA 4412 laminar separation bubble, that goes into this in depth. So if you want to learn about LSBs, look at that podcast. Also, the podcast that we just did, podcast number 29, we also go into the laminar separation bubbles a little bit as well. So they're very common phenomena, and they're very important. And we'll go into it again in this podcast, not as in detail. So if you want to get the details, go to podcast number 11 and listen to that. Moving on. In the abstract, they said, compared with a symmetric airfoil, the low Reynolds number airfoil can delay the occurrence of flow separation and produce more lift in the same conditions. So what they're saying here is the turbulence intensity really affects the complete flow physics and performance of these airfoils. They're very important. So that's why they investigated them. And again, it's not just for experimental, it's for CFD as well. So let's go into depth now into what this means. First of all, let's cover what turbulence intensity means. So we hear it all the time, and it's on wind tunnels. You usually need to quote it when you're doing your research. In effect, what the turbulence intensity is how much the flow fluctuates about the mean. So if you have, let's say, a flow of 10 meters per second, but it fluctuates between 9 meters and 11 meters per second, that's a plus or minus 1 meter per second difference. So that ends up being a 10% turbulence intensity. Now, you can go further into this and unpack it and look at whether the turbulence intensity is random or not. That's another whole field in itself, where you can get sometimes in wind tunnels and just in regular flows, it's not random. So it's not really a turbulence intensity, it's more a periodicity to the flow. But if it's random and it's purely random, then that's really considered a turbulence intensity. So there are some nuances in there, but generally speaking, we can just look at it as how much the flow fluctuates about the mean, and that's a turbulence intensity. And we usually do it in the velocity of the free stream direction. So you do have the turbulence intensities in the other two directions, but they're not nearly as important as the free stream direction for a well-aligned flow, because in a wind tunnel you have your honeycomb, which aligns the flow very well. So you're going to be getting the turbulence intensities mainly in that direction, and that's quite important. So in this paper, to look at the turbulence intensity effects, they looked at 3 different Reynolds numbers and 2 different turbulence intensities. So they looked at a Reynolds number of 26,500, 53,000, and 212,000. So the first one you could say is very laminar. The second one is quite laminar. You can argue that it's getting into the transitional regime. And then the third one, that's between transitional and fully turbulent, depending on the turbulence intensity. And so they did some force measurements to determine what the lift and the drag coefficients were. And the effects of the turbulence intensity are clear as day. So overall, when you increase the turbulence intensity at the same Reynolds number, you get about the similar sort of lift to the stall angle. You get slightly a bit more here and there. It really is a little bit variable depending on the laminar separation bubble. And I'll talk about that in a second. But the main difference is when you hit the stall angle, you then get a much greater lift for the higher turbulence intensity. So what this means is the stall angle of attack has been delayed. It's been increased. So why is that? Let's talk about that. So how does stall happen? When you have an airfoil, you have flow going over it. It will accelerate, and then it would see an adverse pressure gradient, the boundary layer. This adverse pressure gradient is working against this boundary layer to decelerate it. So then when the velocity in this boundary layer near the wall reaches 0 and even reverses, you then get separation. So how can you overcome this? How can you delay stall? An obvious way is to increase the velocity near the boundary layer. So if you look at a boundary layer profile, you look at a laminar boundary layer profile compared to a turbulent boundary layer profile, they're fairly different because the velocity near the wall for a turbulent boundary layer profile is very fast compared to a laminar boundary layer. So by increasing the turbulence intensity, you're accelerating this transition point. So you're making the flow in the boundary layer either very transitional or turbulent even, which means that the velocity near the wall is faster, which means that it can resist this adverse pressure gradient for longer for high angles of attack, which means that you can generate lift at high angles of attack. So in one example here is at a Reynolds number of 26,500, for low turbulence density of 0.6%, the stall angle of attack was 9 degrees. For when you bumped it up to 6% turbulence density, stall angle is now 12 degrees, so it's 3 degrees higher. And this is a very similar thing across the board. Now, I mentioned earlier that at pre-stall angles of attack, the lift was fairly variable. So that came down to laminar separation bubble. So let's talk about that now. So we talked about the post-stall, that's the boundary layer, how this is decelerating and detaching. Let's talk about pre-stall now, because these are two different areas. In the pre-stall regime, the presence of a higher turbulence intensity is not necessarily a good thing for the lift generation. The reason why is because of how a laminar separation bubble forms. So again, if you want to learn more in depth about how an LSB forms and what it is, check out podcast number 11. However, I'm just going to cover it here quickly. What a laminar separation bubble is the flow is first of all laminar to begin with. Then it gets to a point where it's starting to become a little bit transitional and it will detach from the surface. And then it will transition as it's detached from the surface, and then it'll reattach. And when it reattaches, it's already turbulent. And in that reattachment zone is this recirculation zone. And it's very slow moving flow in here. That's an LSB, a laminar separation bubble. What this does is it increases the effective thickness of an airfoil because you now have this dead pocket of air, which the rest of the flow is going over. So in essence, this dead pocket of air is now part of the wing's thickness and camber. It acts like that. So what that does for the pre-stall angles of attack is it bumps up the lift curve slope because you now have a greater thickness. Again, if you want to know more about that, check out podcast number 11, but that's all I'm going to go into here. So that means that when you have different turbulence intensities, that's going to affect the laminar separation bubble formation because LSBs are very delicate. If you change the turbulence intensity even by 0.1%, it can get rid of it completely. It can burst it, it can even form it if it hasn't formed yet. It's very delicate. So you're going to be getting different flow physics depending on whether it's formed, whether it hasn't formed, whether it's shorter in length, whether it's longer in length. And this is all based on not only Reynolds number, but turbulence intensities. So that then will change the lift curve slope in the pre-stall angles. Now, in the drag coefficient, so I mentioned that they also looked at the drag coefficient, not only the lift coefficient. In the post-stall angles of attack, the higher turbulence intensity is obviously better because the flow is staying attached longer. So while the low turbulence intensity airfoil has already separated, you're getting a very high profile drag. The high turbulence intensity profile airfoil has not separated yet. So you're not getting that high profile drag. You're still getting a very low drag. So that's a very large benefit. Now, in terms of pre-stall angles of attack, generally speaking, there was a slight reduction in the drag, but we'll get into that because they break down the drag coefficient, which is very nice. This is something you don't see very often. I actually did my PhD in something similar to this. So it's nice to see other people seeing the value in doing this, and because you can analyze the flow and understand what's really going on. And we'll get into that next. So let's move on to this next graph, figure 11, for those of you playing at home. In figure 11, they have the drag coefficient breakdown for the NACA 0012 and the SD 7037. For both of them, the effects were fairly similar. What they did was they broke down using CFD the drag coefficient due to the pressure drag and the drag coefficient due to the friction drag. Now, across the board, for a higher turbulence intensity, the pressure drag is lower for the high turbulence intensity foil. So that's good news. There were a couple angles of attack where they were similar, but generally speaking, they were lower. So that means that increase in the turbulence intensity decreases the profile drag, and it decreases a lot. Now, interestingly, when you increase the turbulence intensity level, the friction drag increases though. So you get that trade-off where you get a reduced pressure drag, but a higher friction drag. Now, the benefit of a high turbulence intensity is that because on an airfoil doesn't have that much friction drag compared to the pressure drag, the reduction in the pressure drag is greater than the increase in the friction drag, which means that overall, a higher turbulence intensity will reduce the drag of an airfoil in these Reynolds numbers for these two airfoils. So that's pretty cool. And then obviously in the pre-postal region, because you have for the high turbulence intensity, you have an airfoil which is still seeing attached flow. The profile drag is far lower because the pressure drag is very low compared to the low turbulence intensity airfoil, because the boundary layer for the low turbulence intensity airfoil is much more laminar than the high turbulence intensity airfoil. So just right there, I want to stop and say to make sure to check out the instruments we make here at Aerodynamics. We make stuff to make your experiments better. We make stuff to measure the density of your air that you're using in your experiments much more accurately, so you don't have nearly as much error. And it also makes CFD validation far easier. We also make traverses. We also make PRB systems, so check them out. We also put on courses to make you a better analysis. We do CFD, experimental and theoretical, so you can learn all this stuff and get better. And we also put on a conference every year. It's called the International Aerodynamics Conference for aerodynamicists to get together and talk about aerodynamics. We talk about this stuff and lots of other stuff. So check all them out, links in the description. So back to this paper and this idea of the turbulence intensity. So we've now covered how the turbulence intensity affects the lift, how it affects the drag, how it affects the components of drag. So I just want to quickly come back to the components of drag to explain them for those who don't know. So the drag coefficient is made up of a bunch of different components depending on what flow you're seeing. You can not only have the friction drag, which is the resistance that you get when flow goes over a surface. So we all know friction. We've learned it from birth effectively, where you have your hand on a table, for example, and you try to push it, you get some resistance because the bumps in your hand are aligning with the bumps in the table and they get stuck on each other and blah, blah, blah. So that also occurs for airfoils. You have friction drag for the fluid moving over a surface. There's also something called pressure drag, and this is the difference in pressure on the front side of an object to the back side of the object. So that difference creates a force, because pressure is just force over area. So that difference creates a difference in force, and then you get that resistive motion. You also can have something called induced drag. This is for airfoils mainly. So when you produce lift, you generally get something called induced drag, and this is characterized by vortices that are forming at the wing tips. Or there are some flow control devices. I'm not going to get into them in this podcast, but you can see vortices in different areas. They're generally speaking induced drag. Now, in different applications, for example, on cars or just cylinders, for example, you can get other things just called vortex drag, and they're akin to induced drag. The mathematics works out very similarly. And even though they're not the same underlying principle, you can measure them in the same way and calculate them the same way. Again, these are just vortices, and vortices, generally speaking, are just dead energy. You're wasting energy. So that's another form of drag. And then you get wave drag, which is when you go near the speed of sound, or if you're swimming in a pool, again, you get the fluid above, it creates waves. With the speed of sound, you get this compression of air in front of you, and they're generally characterized as wave drag. Again, they're different concepts, but they're different components of drag, and the total drag coefficient is made up of all of these components together. Now, in a lot of applications, you're not going to have wave drag, you may not have induced drag, but you're going to have friction and profile drag and pressure drag. So it really depends on the application. And then profile drag is generally just the summation of the friction drag and the pressure drag. So in aeronautical engineering, we say profile drag as the overall drag of an aircraft that isn't producing lift. Also called parasitic drag, and there are other terms and definitions to them, but that's a mini crash course on the different components of drag. So let's move on, because they talk about now, we've mentioned earlier at the start how the turbulence density affects the transition mechanism to turbulence. So what this means is that we mentioned the dynamic separation bubbles, and they form because you generally have a low turbulence density and a transitional Reynolds number. Dynamic separation bubbles are generally seen as a delicate way of transitioning to turbulence. You can get very low turbulence densities, which then result in these dynamic separation bubbles forming. We can have high turbulence densities, which then create a very big disruption in the flow, and then you get turbulence forming very quickly. So there are many different ways that you can transition to turbulence. This very high turbulence density path is called bypass transition, and then the dynamic separation bubble formation is seen as, again, a very delicate one. So by having a high turbulence density level, you then change the mechanism that you go through to turbulence. So this changes the flow physics. So that's what they mean there. So now let's move on again a little bit to another aspect of these turbulence densities. They say from the evolution of flow separation on the upper surface of the airfoils at turbulence density of 0.6%, it can be concluded that the increased angle of attack results in the increase of adverse pressure gradient around the trailing edge, contributing to the separation of the boundary layer. So that's obvious. When you increase angle of attack, the adverse pressure gradient increases. And then they go on and say, the separation point moves towards the leading edge until the complete high angle attack angle separation still happens. So again, because you increase angle of attack, this adverse pressure gradient increases, and that means that less and less of the airfoil's suction surface, generally the upper surface, is seeing an attached flow. And they go on and say, now they compare the higher turbulence density airfoil. They say, however, the airfoil's aerodynamic performance improves and the process of separation is suppressed at turbulence density of 6%. In general, the greater turbulence outside the boundary layer enhances flow stability, injects energy into the upstream laminar flow around the airfoil, and enhances the ability to resist adverse pressure gradients so that the laminar flow separation could be delayed and overcome. So let's unpack that sentence, because there's quite a few things in there. They say the greater turbulence outside the boundary layer enhances flow stability. So that's directly related to the laminar separation bubble, because I mentioned how LSBs are very delicate. If you change the turbulence density, it can really change it very dramatically. And even angles of attack changes it dramatically. So by having a high turbulence density level, you can get rid of the LSB and make your airfoil much more predictable, much more stable. So that's what they mean there. They go on and say that the high turbulence density also injects energy into the upstream laminar flow around the airfoil. So that, again, is true. You have a higher energy in the boundary layer, and you're also going to be able to overcome that adverse pressure gradient easier. And overall, they say this enhances the ability to resist the adverse pressure gradients so that the laminar separation can be delayed and overcome. They go on to another mechanism. They say, then the high energy fluid in the free stream is brought to the near wall area in the flow mixing process. So what they're saying is this high turbulence density is also then dragging high energy momentum into the low area in the boundary layer. So this is a very interesting thing. This almost acts like a vortex generator on aircraft. So this is a very amazing find. So one thing I want to talk about that is how turbulence breaks down. So as I mentioned earlier in the podcast, this podcast is turning into a bit of a very intense one, and I'll probably have to go back and revisit some of these topics later on. But let's now talk about how turbulence breaks down. So earlier in the podcast, I said the turbulence density is generally just measured in the free stream direction. But here they're saying that even though you have this turbulence density in the free stream direction, you have higher energy fluid in the up in the flow being brought down into lower in the flow near the wall. This isn't perpendicular to the free stream direction. So how is the turbulence density in one direction affecting how the flow is moving in another direction? That's a good question, and we'll talk about this right now. So turbulence breaks down three-dimensionally. There's a law that says even if you have two-dimensional turbulence, that will break down three-dimensionally. So even if you don't have any disturbances in one direction, the breakdown of features and the transition to turbulence will then create a three-dimensional effect and drag fluid from other regions. And that's what's happening here. So that's very cool. Then they talk about how the separation point transition changes between the high TI and the low TI, so the high turbulence and low turbulence, and in effect, it just delays separation. So instead of, for example, at one angle attack, they said that the flow separates at 5% of the chord, and now it's being delayed. And they conclude saying it can be said that the increasing Reynolds number results in early transition and reattachment of this laminar separation bubble, contributing to an overall decrease in the separation bubble length. So again, as I mentioned, this all affects the LSB, the Reynolds number, and the turbulence intensity. They go on and say the effects of turbulence intensity mainly appeared to be that with the increase of turbulence intensity, the aerodynamic performance of airfoils become more stable, the lift improves, and the stall angle increases. And the LSB can be suppressed to some extent because it's a very delicate phenomenon. Now, one thing that I want to talk about, the last thing to cap off, is under natural laminar flow separations, the distance from flow separation to reattachment of an LSB is 50,000 Reynolds number. So if you look at the distance that it covers, an LSB is typically seen at 50,000 Reynolds number, if you calculate that with the length of the LSB being the characteristic length. Now, this is not a hard and fast rule. I've seen numbers from 50,000 to 70,000, even lower, maybe 40,000. It also depends on the turbulence intensity, as this paper is attesting to. We've seen now that turbulence intensity really does make a big effect, have a big difference on the flow physics of an airfoil. So what does this Reynolds number mean? It means if you have a surface which you cannot have a Reynolds number 50,000 or higher, it means that an LSB will not reattach. And this is important for dragonfly wings, for example. So dragonfly wing is typically exposed to a Reynolds number of 70,000. This places it right in the juicy range to have an LSB forming on it. That's problematic because that means it becomes unstable, because depending on the different flow conditions, you can get a dramatic loss in lift when the LSB pops. So the way that dragonfly has overcome this is on making its wings very crinkly, that then introduces disturbances and gets rid of an LSB. So this is one little technique you can do if you have a Reynolds number on your flow, on your object of around 50,000 to 70,000. It means you're in the prime region to get an LSB forming. To get rid of that, you can then introduce some turbulence on the surface to then stop the LSB forming and making your object, whatever it is, whether it's an airfoil or even just a table, more stable. So that's the takeaway message here. So that's the end of this podcast. Make sure to like and subscribe this. Check out everything we do at Aerodynamics. Check out the instrumentation we do. Check out the courses we put on, and check out the conference we put on. All the links can be found in the description. So peace out.